that loss, that amount that the neural net missed, and figures out how to update every single one of those weights in the neural net so that next time the neural net won't miss by as much. But we'll make this all precise with code in just a second. So the key point from last time is there's really just one key concept that makes neural nets work. Because neural nets are these nested mathematical functions, the reason that they can actually learn through this process is because of the chain rule from calculus. Because we can figure out how much each of those weights is contributing to the neural net's loss using the chain rule and then update those weights accordingly. So we can do basic neural nets. That's great. All right. And we can actually solve a classic image recognition problem using this. The MNIS problem is where there are 70,000 handwritten digits. And by the way, you might have noticed I'm using this thing called, I'm using a Jupyter notebook, actually to generate the slides here. And I'm using something called reveal.js to turn what's in my Jupyter notebook into slides. So I'm actually going to be running code live today. So this is actual code that's running. So I just imported a bunch of stuff. And I'm going to read in the MNIS data from the library sklearn. And that actually reads in the data. And reads in, and I know this is a little small because of the shape of the room. This is sort of a room that goes back. But it says there's 70,000 images we've read in. And I'm just going to split that into a training and testing set. We're going to use the same training and testing set throughout all the examples we're going through tonight. Setting aside 90% of my data that I'm going to train the neural network on, keeping aside 10% for my testing. Well, let's just visualize the images to talk about what I was talking about, that these are really just numbers. So each image is actually 28 by 28 pixels, and each pixel value has some value between 0 and 1, depending on how dark that pixel is, ranging from all the way dark to all the way light. And let's not forget about that sigmoid function. We can train a neural net, and I walked through each one of these corresponds to an equation that is involved in actually just training a really simple neural net on these images. Now this looks really complicated, and it is, but each one of these is actually a fairly simple calculation that you can arrive at through sort of the equations underlying a neural net. And I apologize because most of you weren't at the talk in March, but I went through this in detail in March and showed how basically you can actually train a neural net even to do this really complex image recognition problem in really 20 or 25 steps, because each one of these is just one step.
How specialized is this to your project?
All this takes in is a number of inputs and outputs a number of outputs.
Okay, so that's,
Yeah. We'll answer all these questions throughout.
So it's really generalized.
It's very generalizable. So now I'm just defining a predict method. So this takes in an input and on a neural net we've already trained actually predicts what image it is. And now let's actually run it. So right now, that code that I just ran, this is really running on my computer. It's taking in the training data, the X data, the image data, and the actual values of what classes these belong to, and making a bunch of predictions. And let's see how accurate that was. It turns out it's 91.3% accurate. So just by randomly initializing some weights, running this neural net through these 25 lines of code, it's pretty crazy that we can solve this really complex image recognition problem with 90% accuracy. So that's good to know. 91.3% accuracy, 8.7% error. Not bad, but we can do a lot better. So we missed 8.7% of the images, and by the way, we just trained this network for one epoch, which means we ran every image through the network one time. But, I mean, people are getting definitely above 99% accuracy, less than 1% error rate, using really cutting-edge techniques. Yeah.
How many layers does the neural network have?
That had only one hidden layer, but we'll get to all this. I love these questions you guys are asking. And by the way, this talk will be on GitHub. In fact, it is on GitHub, and these are actual links, so you can click this link and go to this website and look at other networks. But okay, how can we do better? This is really getting into the meat of it. So this is where the sort of craziness of neural nets comes in. So there are lots of ways we can do better, right? We can build deeper nets. We can add more layers. We can change our learning rates. We can add learning rate decay, learning rate momentum. We can do all that stuff. We can add dropout. I mean, who wants to yell out some other neural net buzzwords they've heard that they think might help us train this network? Go for it. Come on, don't be shy.
Early stopping.
Early stopping. Okay, do a shot. Yeah.
Pick a different activation function.
Different activation function. Excellent. Excellent idea. Regularization. There we go. Other buzzwords you've heard. It doesn't even have to be right. I want actually all of the things that have been said so far have been right. I want someone to yell out a wrong buzzword. Come on.
Augmented data set?
That's actually right. So good try. Very good. It's a good idea. So you're wrong.
Mary Poppins.
What?
Mary Poppins.
No, Jeremy. That's too.
You said wrong.
Come on.
Okay.
Give me a better wrong one. Come on. Someone's got to have something.
Associative learning?
Associative learning. There we go. We could use associative learning here. That might actually be a thing. It really might be. I might just not know of it. So I think with neural nets, are you overwhelmed yet? So if you're here to learn, you're probably like, wait, I actually want to know what these things are. Why don't you teach me instead of just saying that there's lots of things you can do? I think with neural nets in general, there's sort of a paradox of choice. There are so many things you can do with neural nets that a lot of people just take tutorials and take the pre-built things that are found that you can find online and just try to run their data through those instead of really understanding what's going on and trying to break them things down in a systematic way. And that's what I just said. So if we look at things individually and learn a little bit of theory, we can actually peek under the hood and help understand how neural nets are actually working better. All right, let's start with, I'm shocked no one said deep learning. Come on, guys. I was at a data science conference last summer, and the guy was like, take a shot every time someone says deep learning throughout this conference. All right, another thing is, and basically everything I'm going to show tonight is built from scratch. So I've only imported NumPy. We're not using TensorFlow or Keras or any of that stuff, because I really believe, I love this quote, what I cannot build, I cannot understand. So if you want to really understand what's going on, you've got to build this stuff from scratch. So before we just, so first of all, oh, Nathan's standing in the back telling me to speak louder. Can you guys hear me a little better? Cool, so even more. So before, we described a neural net as just a function that passes input through and generates output. Now we're going to have to describe a neural net a little bit differently so we can start thinking about what it means to have a deep network. So before I coded up those steps, those 25 steps that allow us to learn a neural net, if we wanted to have 3 or 4 hidden layers, that would be a ton of steps. I definitely wouldn't want to do that. So instead of thinking of neural nets like functions, we'll think of them as like layers, like a series of layers. We'll think of a neural net as taking an input and passing its input through a series of layers, each of which both has a linear component, a component where weights are multiplied by the input to that layer, and an activation function, a function that does some nonlinear transformation to the result of that linear transformation that creates that makes the network nonlinear. And just terminal, yeah.
So I've been thinking about layers quite consistently recently, and I don't know if this is the right place for this question, but if I had a neural net that produced a numerical figure, I want to take that numerical figure and put it into a natural language chatbot that is also driven by machine learning, would it be a layer for the numerical actor, a layer for the natural language chatbot, or would it be a bunch of neural network layers for one function with a bunch of neural network layers for the other function?
There are several ways you could do it. You could use something called a sequence-to-sequence model, which are the cutting edge for chatbots. We'll talk afterwards. Something I should have said at the beginning is I'll stick around for as long as people want to come ask me questions about this. This is my passion. I'm here on my own doing this. I love this stuff, so we'll talk afterwards. Yeah, ask afterwards. All right. Layers that are neither input nor output are called hidden layers, and sending the errors backwards through the network is called backpropagation. All right, so how do we code this up? This is where it gets interesting. Well, we'll define a neural network class that takes in a list of layers, which is itself a class that does a bunch of stuff. And here's the neural network class. So it takes in a bunch of layers, and this might be a little bit hard for people to see because I know it's a little small. apologize for that. All this code, including the talk, will be on GitHub, including the notes in between the slides. So it takes in a series of layers, and and this is the key thing. This is what a neural net does. For each layer in the network, to make a prediction, it takes in the input. For each layer, it does a forward pass through each layer and ends up with some output. Then it computes the loss at the end of all the layers, and then it sends that loss backwards through each layer backwards. Notice that this part here is for layer in reversed, which means when we do the backwards pass of the neural network, we're going in reverse through these layers. And again, this is real code that's running in this notebook. Let's do the layers. So this is the basic framework for a layer. Each layer has to be able to send input forward and send it backwards, right? And I will give props to this guy. The idea of defining layers in that way comes from this guy's GitHub. He's a student at the University of Denmark, and he has a bunch of phenomenal examples on his GitHub. That's a real link there that you can go check out, so I had to give props to him. But this stuff is all sort of from that mathematical understanding of neural nets. So basically, every layer gets a number of neurons that it takes in, and a number of neurons that it outputs, and it has an activation function. Meaning, and these activation functions are things like sigmoid, ReLU. They basically take in any random number and squash it down into either between 0 or 1 or -1 and 1, and they do so in a nonlinear fashion. There's more on activation functions, and I'm happy to explain that more at the end if you want. But so each layer takes in input, generates output, and sends things through an activation function, and it does so in an intuitive way for the forward pass. For the backward pass, it gets pretty tricky because there's all these derivatives floating around, because you have to figure out, given that I've gotten input in my backward pass, how much should I update the weights in my network? How much should I update the weights in my layer? And it turns out when you break down those 25 equations that were the entire network, and when you break it down layer by layer, and I went through my talk last time, and there's slides online of like all the equations of why the calculations have to be like this, but it turns out that this is the way to update your weights. You have to calculate the derivative of the activation output relative to the input, the derivative of the input relative to the input to that layer, etc. So I apologize that I'm not going in depth into that tonight, but I'll link to slides on that, and just trust me that that's how the weights should update.
You have a blog on that too, right?
And I have a blog on it too, SethWeidman.com. But actually, and let's not forget about our activation function. So every layer is taking the output of that linear transformation, the multiplication with the weights, and feeding it through this sigmoid function. We're just using sigmoid tonight as our activation function. We'll do cooler ones in the future, because sigmoid's easy. Sigmoid is just takes any real number. It's the one that looks like this. It takes any real number and squashes it down to between 0 and 1. So anytime your network is outputting probabilities, it's a good one to use. And we can run this. So let's define 2 layers, and let's define our neural network. Neural network, layers, I'll feed that in, and I'll give it a random seed, so I know it generates the same output every time. And I'll define what it means to make a pass through the network. It means go forward through the network with an observation, compute the loss, and then back propagate that loss. And that's all it means to make a pass through the network with this framework. And let's run this. I'm doing some things here like randomly shuffling the order that I'm going through the images in my data set. Then, this is where the work is actually going to happen. I'm going to actually do a neural net pass on every image on this data set. And because of the way the weights were randomized, and because of the way these, because of the order I went through the images for this specific neural net, the accuracy here is only 82.3%. So it's lower than it was last time, just because of randomness. And I'm going to use these same weights to compare different neural net things going forward. So a different random weight initialization gave us just 82.3% accuracy. All right, and if we turn, I'll use this function throughout. We just turn what we just did into a function that takes in a neural net, takes in a data set, and outputs what's the accuracy. This is a function that does that. All right, now let's answer Nick's question. What happens if we do deep learning? What happens if we build deep networks? Does it actually improve accuracy on this data set? Well, since we have this framework sort of from scratch that we can easily put together different kinds of networks with and try things out, let's actually try that out. All right, so let's define a bunch of layers. And that does that. Let's define a function that for a different set of layers prints the accuracy of a neural net with those layers. Yeah, Nick?
How many neurons do you have in each layer?
That's a great question. I have 50 in each layer.
Okay.
I found that for one layer, one hidden layer, 50 worked best. But you could actually play around and try a lot. You go crazy with that hyperparameter.
One more question, so if you got
Yeah.
50 in each layer, I'm sure you're multiplying, so what is the aggregate function of that?
That's a complicated question. It's yeah.
Because you know the layers interact with each other, so you're going from layer 1, layer 2, layer 3, or you're going layer 1, layer 2, layer 2, layer 3, or layer 1, layer 2.
Yeah, I mean, the way it's going to work is the first layer is 784 because it's the number of pixels.
Okay.
That's going to be multiplied by a 784 by 50 matrix to turn it into the second layer. Then the second layer is going to be multiplied by a 50 by 50 matrix to turn it from the second layer into the third layer. And then eventually the last layer is going to be multiplied by a 50 by 10 matrix, and that's going to output 10 probabilities. Probability of that image being 0, probability of that image being 1, probability of it being 2, etc. That's the way it's going to work. Okay, let's actually live test out some deep networks. Whoops, just broke it. No, I think I know what I did. There we go. This is my first time using this reveal.js thing. All right. So with one hidden layer, the accuracy was 82.3 from before. So let's see, what do you guys think? Is deep learning going to win? Are we going to get more accuracy with more layers? Yes? No?
Yes.
Yeah?
Yes.
Yes? Yeah, 90.7. So again, with that same weight initialization, we got higher accuracy with more layers. And note, where am I feeding in more layers? Right here. Okay, what happens if I keep adding layers? I could just keep adding layers here, hidden 2. Oh, that looks like the accuracy goes down a little bit. So I can't just keep adding layers. There actually is a point of diminishing returns, at least with this neural net architecture. So that's sort of interesting. And again, this code is all, you could add 10 hidden layers and see what happens. I haven't actually done that. Email me the results when you do. And it looks like that got cut off, but the accuracy of 4 hidden layers is about 87. So it's even lower. So this seems to be the sweet spot. This one where you have actually 2 hidden layers in that network. Sort of interesting, right? So deep learning can help, but we really need more tricks and more understanding to really get neural nets working well. All right, let's talk about some stuff we can tune. So I think a great place to start in terms of tuning neural nets is the learning rate. Why? Gotta look under the hood. There we go. Yoshua Bengio, one of the top 10, if not top 5 neural net researchers in the world, says the learning rate is the single most important hyperparameter, and one should always make sure it's tuned. So, okay, I trust him. It's fine. All right, let's tune some learning rates. So let's add to this class and add the ability to tune learning rates in there. So first of all, I think coding things from scratch and building things really makes you understand, well, what is a learning rate? Well, a learning rate is actually a very simple thing. There's a very simple change we're going to make to this. First, in the neural net class, we're just going to add the ability to add a learning rate to that class. And then I'm going to assign that learning rate. This is not the important part, but I'm going to assign that learning rate to each layer in the network. So each layer now has the ability to access that learning rate. All right, that's just step 1. Now, here's the fun part. All a learning rate is when we update our weights in this line down here, we are taking our weights, which is some matrix for each layer, and we're subtracting some weight update that weight update is making the loss reduced. All the learning rate is just multiplying that matrix that we're using as our weight update matrix by some number. That's it. It's nothing magical. It's nothing like that we can't understand. It's just a simple multiplication of our weight matrix by a number. And we can sort of, as we're going to do, look empirically at what effect that has on our learning rates. So let's, almost giving away the answer. So let's run a function that runs a bunch of neural nets with different learning rates and see what the accuracies are. And this will give me an opportunity to get one. Where'd the water bottle go?
Is that it?
I don't know if that has water in it.
It's under your desk.
Oh yeah, there it is. All right, what's going on? Okay, so the accuracy of a network with a learning rate 1 over 10,000 is basically no better than random. Oh yeah, that's probably really small. That says 9.7 there, so 9.7%. So random guessing, since there are 10 classes here, would give us 10% accuracy. This is 9.7. As our learning rates get higher, we get higher accuracy. This just means that we're giving our network more capacity to learn. We're learning faster. As we get up to 0.1, we get almost 90% accuracy. And a learning rate of 1 gives us that 90.7% accuracy that we saw before with our neural net with 2 hidden layers. Let's see what happens with our learning rate of 10. So we're giving it huge weight updates each time. Okay, that really kills our network. So you can play around with that and see how learning rates affect your network. And you can try, and I tried this like, what if you do a learning rate of 0.5, 0.33, 2, 3, any of that stuff. Go ahead and try it. Now let's get fancy a little bit. I'm gonna keep going actually. I'll answer questions because I'm on a roll right now. This is where it gets fun. So this is stuff that's not easy to do in a lot of the popular neural net libraries like TensorFlow or Keras. You can play around with things and try different stuff and see what happens. So there's a common problem with neural nets called the vanishing gradient problem. And if you think about what happens in when a neural net when a backpropagation happens, at each layer there's the amount that the loss changes as a function of the weights, the partial derivative, is multiplied by some number. And the most that number can be multiplied, if we're using sigmoid activation, the most it can be multiplied by is negative 0.25, because that's the maximum slope of the sigmoid function. In practice, a lot of times it's multiplied by an even smaller number. And so what happens is the weight updates get smaller and smaller as you go further and further back in the network. So how can we fix that? Let's try this. What we're going to do is this. We're going to give our network, and we can do, and normally in Keras or TensorFlow, you give your whole neural network one learning rate. Well, there's no reason in theory why you can't have different learning rates at different layers. You could have one layer have one learning rate, because the learning rate is just a thing that the weight update is multiplied by. You could have another layer have a different learning rate, and another layer have a different learning rate. So that's what this does right here. This says, go through, when you're setting up the neural net, go through all the layers, and whatever learning rate you fed in, that first layer, the one that's input to the first hidden layer, don't do anything to it. The next learning rate, divide it by 10, and then the one after that, divide it by 100. So basically make the learning rates get smaller and smaller as you get closer to the weight, the layers that are going to be getting the biggest updates naturally. So run that. That updates our neural net class. And let's try this out. There's that. And all that was, let me actually go back. All that was actually that was the same function from before, but you'll see it has a different print statement. And all right, let's try things out. So the first neural network is going to be one that has, what you'll see. All right, so first we looked at a net that has a learning rate of 0.01 in the first layer, 0.001 in the second layer, and 0.0001 in the third layer. So those learning rates are way too small, only 9.7% accuracy. Then we get a lot better when we use the next the next learning rate up, so to speak. And we actually get an accuracy that's significantly higher when we do this learning rate, varying the learning rate by layer thing with a learning rate of 1. So we use a learning rate of 1 in the first layer, 0.1 in the second layer, 0.01 in the third layer, we get an accuracy of 91.8%. So that might not seem like a big increase. One way to look at that is only a 1% or 1 percentage point increase in accuracy. But another way to think about it is it's basically a 10% reduction in your error rate. Your error rate went down from 9.3% to 8.2%. So it went down significantly. So having a higher learning rate in earlier layers versus later layers does help accuracy in this case. And again, writing this from scratch, you can be as flexible as you want, and you can try different things out easily to see what actually helps your neural net. All right. I'm going to go a little faster since I want to leave time for questions, and I think I'll just go a little faster. It's getting hot in here. They can just open the window. So, learning rate momentum. Another thing we can do is if the weights are continually getting updated in the same direction, in iteration after iteration, we can make the neural net actually take that into account and learn faster. So weight updates are really good doing gradient descent, so they're figuring out where the bottom of the hill is, and if a ball is rolling down the hill, guess what? It has momentum, it doesn't just have velocity. So, So if our weight updated each time is u, if the amount we want to update is u, we could just update u, or we could update basically u times some amount that u was updated in the previous time step, plus some amount that it was updated in the time step before, etc. And this is called, and with a decay parameter in there. And this is equivalent to basically, and is often described as increasing your learning rate when things are going in the same direction. So it's sort of all still tuning the learning rate. How do we implement momentum? First, we just add a momentum parameter to our, actually, this is the key part. So momentum's kind of an interesting one. There's actually sort of a simple and easy way to implement it. So what you do is you initialize your neural net with this thing called velocity, which is a weight update matrix that's all zeros, that's the same size as your weight matrix. And the first time you update your neural net, you assign your velocity matrix to be some momentum parameter, so 0.9 times whatever that neural net update was. So after your first iteration, your velocity, so to speak, is 0.9 times your weight update. Then, the next time you update, you do 0.9 times that velocity plus 0.9 times plus your new update. And so the effect of doing that is you get that equation that I showed before, where you have a decay parameter that is making the neural net take into account less and less over time what's going on as you go further back in time. And yeah. So you can test this out, test out different parameters. And what you see is actually you don't get a huge increase in the accuracy of your neural net in this case when you do momentum, but you do get a small accuracy increase when you use momentum of 0.5. But momentum, like this, it's cool to see how to implement it and know that you can do it from scratch, but you don't get a huge boost from it here. So there is a practical lesson here too of throwing the kitchen sink of problems at a neural net problem isn't always the best approach. And indeed, if you had chosen the wrong momentum parameter, it would have been extremely harmful. So a momentum parameter of 0.9, which is a very standard one to use, makes the network a lot worse. Yeah, there's more stuff on there. So I'll go through quickly a couple more tricks that are fairly easy to implement with this framework. So dropout is one you've probably heard of. It's a technique to prevent overfitting in networks. And every time you make a forward pass through the network, you randomly choose some portion of your neurons and just set them to 0. And you say, we're not going to look at those through this pass. And what that does, it sort of has the same effect of using a random forest. It prevents your network from overfitting, and it can force it to generalize to, it can not generalize, it can force it to learn redundant representations of your data. So if there's a subset of neurons that's learning what all the ones are, and you take some of those neurons out in one pass, then other neurons will have to pick up the slack and learn what the ones are in the neural nets. Here's how you implement it. Essentially, you take at each layer, every time you're going through a layer, you take half the neurons and you set them to 0. This code has a bunch of, you have to reshape it and do all this stuff to get this to work in NumPy, but that's, those are just sort of NumPy details, and you can have a look through that on your own. And one sort of important thing with dropout that some of you may be aware of, some not, is we do what I just talked about when we're training the network. When we're actually seeing how well the network performs on new images, we don't use dropout. We use all of the neurons that we've trained. So what I have to do here when I'm training my network, when I'm testing my network, is I have to set the dropout of the net to none. So set there to be no dropout before I actually test how good it is. And doing that, basically, you see that dropout doesn't really help in this case. This net, which is a fairly shallow net for image recognition and only uses 2 hidden layers, is really more like underfitting our data. It's not really overfitting the data. And adding dropout did not improve accuracy. So there's sort of a fun one I wanted to do at the end, and I'll let you look through it. It's called drop connect. And if you look at the MNIST performance, the different nets performance on this is actually the one at the top. What's interesting about this technique is it's not in TensorFlow. So it's not in any of the popular neural net libraries. You can't do drop connect on a network using TensorFlow or Keras or any of those libraries. But it's actually really easy to implement. It, again, sort of has the same issue as dropout. Our network's not overfitting, so it doesn't really help in this case. But it's pretty easy to implement. So at each, so that's dropout. So this is a little helper function that takes in weights and does a bunch of reshaping and detailed stuff that is really just NumPy specific. It takes a bunch of weights and sets half of them to be 0, or sets 0.1 of them to be 0. And once you've done that, when you're going through each layer, you take, if you're using drop connect, you get your drop connected weights, which are just their weights with a drop connect parameter applied, and then send that through your activation function, and that's how your layer sends stuff forward through the neural net. And similarly, if we're using drop connect, we have to set that to none when we're passing things through the network and we're testing how good our neural net is. So, sort of an important thing. All right. And it turns out it doesn't really help here. You can, again, run all this code. This is a live Jupyter notebook, so trust me, these accuracies are real. Yeah, drop connect doesn't really help in this case, but you can see that it's a cool sort of cutting edge trick, and it's not very hard to implement. Hopefully you feel a little bit more like you can go and actually tinker around with the internals of neural nets yourself now. So training neural nets involves a lot of tricks. And at least for those of us that like to know how things work from the ground up, and to really solve hard problems. If you're ever doing machine learning for a class, for a company project, for something like that, and you really want to get into details and solve the problem, knowing these tricks is extremely important, and really knowing what's going on. So this has been a long journey for me, since not knowing anything about neural nets to doing this. And I'm excited to continue it, and I'm excited to add more stuff to this. So in the future ones, I plan on doing different activation functions, different weight initializations, and all sorts of stuff. So come up to me with feature requests after this if you want. And the real gold mine that each of these will require a talk in itself is doing convolutional neural nets and LSTMs from scratch. So that'll be fun. Next step for you, go to the GitHub repo for this talk. It's right here. It's I could send you all the link to this talk, but never mind. So star the repo, fork, and contribute. One more thing, there was just a big Apple announcement yesterday, so one more thing. Breakthrough announcement. Jeremy and I are launching a podcast. A breakthrough revolutionary podcast. The tentative title is The Neural Net Guys. Some of you may be guests on this podcast one day. You can aspire to be guests on this podcast. It's amazing. Actually, no, seriously. We need guests. So, yeah, if you could be guests on the podcast, we'd really appreciate it. We might even pay you. Jeremy might pay you. That's it, guys. Thanks for coming. Yeah, we're not going to do a formal Q&A, but I will literally stick around and keep talking about this stuff as long as you guys want. So, thanks for coming. Yeah. Hey, appreciate it.
Thank you for this.
Nope. What's your name? Shell.
I'm actually I'm doing the Stanford right now.
Awesome.
So
No, I downloaded by
very easily.